Yeah. Yeah.
Okay, everyone, we're going to get started. George, take it away.
Yeah. Well, thank you all for coming today. I'm really excited to introduce to you Dr. Zachary Michaels, who will be the colloquium speaker today. I'm excited about having Zach do this colloquium. I think he's got some areas of expertise that might really help you with your research, teaching, outreach activities here in the department. And you'll see during this talk that there's sort of two areas of expertise that you might be able to connect with. One is with the scanning electron microscope that we have in the basement downstairs. Zach has expertise with all of the different detector systems that you have on SEMs, especially the EDS and Ebsd systems, which we really have never had a lot of expertise with. So kind of brand new capabilities with the SEM. And then, as you can see from the title of his talk, Zach has high-level expertise in microstructural analysis using the SEM. That's kind of the connection between those two. And so I think Zach is going to have a really big impact on how we do our research and teaching and different activities here in the department. Let me tell you a little bit about Zach's background. He came from San Jose State, where he completed his bachelor's and master's degrees, and then went to the University of Wisconsin, where he worked with Basil Tikoff on a PhD. And that was different. It was kind of the focus of this talk. It was developing methods of microstructural analysis. I think that was kind of the start of what you'll be talking about today. During that PhD, he developed the different techniques and also established lots of collaborations with researchers who use these different methods. He then completed that work and stayed at Wisconsin for an extra year, where he was one of the original designers and programmers on Spot, if you're familiar with that. It's kind of a new cyber system for archiving and handling three-dimensional earth science information, and also Strabo Micro, which is kind of the micro equivalent of Strabo Spot. And then he left Wisconsin and did something very different. He went off and became an SEM sort of technician engineer. He worked at a Seagate factory where he was in charge of 12 dual beam SEMs that I guess were running like 24/7. Yeah. So that sounds a little stressful in those machines. So he learned a lot about the nuts and bolts of SEMs during that time. And then he went to the University of Minnesota, where he did a 2-year postdoc in the rock and mineral physics lab at Minnesota, working on natural and experimental samples. And then we were really fortunate to have him come to the U of A in July. He started with the LaserCon lab downstairs in July. He's now the manager of the SEM lab, and we hope that he will establish lots of collaborations with you all in the room here and people on remote connection in the department, and also help us move into the world of microstructure, microtectonics. This is kind of an area of research that we've never had much expertise in here in geosciences. So I'm excited about Zach being here and Zach's talk today. Jump in.
Thank you, George. That was great. Yeah, so thanks for having me here and for organizing this and let me talk. I'm really excited to be in this department. As George mentioned, I am eager to help with people's research. One of the things that I've been doing the last couple of years that I've enjoyed the most is taking some of these things that I've worked on developing and really helping people implement them for their own projects, whether that's simple sort of microstructural image analysis or some of the more microkinematic kind of things that I'm going to talk about today. So yeah, the title of my talk, Microtectonics of Natural and Experimental Rocks. I'm hoping I will actually get to some of this, but I wanted to be sure to take an opportunity to talk a little bit about the lab and what we're doing there so that you know what resources you have available to you, and then use that as a transition into some of my research. I just wanted to quickly throw these up so I forgot to bring the books up, but put these on a slide to help give some context. I'm going to talk about a lot of things that it dawned on me maybe aren't things that get talked about a lot in the department if there aren't other people doing a bunch of microstructural work. And so these are 3 of my favorite books that I use as references. And so for other grad students that are interested in microstructure, I would check these out. The Microtectonics, this book is, this is in its 2nd edition. It's a little bit outdated now as of the 2nd edition in 2005, but a lot of the concepts that I'm going to talk about today really are framed and summarized well in this book. This book, if you're not familiar, A Practical Guide to Rock Microstructure, is just an amazing book of all kinds of different microstructural micrographs. So from igneous rocks, metamorphic rocks, tectonites of different kinds. So it's really useful resource. And then for a lot of what, whether we're doing electron microscopy or optical microscopy, a lot of the analyses that we end up employing there are many that are based on image analysis. And so Renee Hilbronner and Steve Barrett's book here is another great resource that really lays out sort of the math or the concepts behind how you would undertake some of these kinds of analyses. I'm also just going to mention a paper quick here by Davis and Titus. This is a couple at Carleton College. Sarah Titus is a structural geologist, and her partner Joshua Davis is a mathematician, and they work together a lot on sort of linking things about structural geology and microstructural geology and tectonics in a mathematical way that then you can actually use. And so this is a really crazy figure. I'm not going to walk through it, but I love this figure because it's a resource that literally connects all of the kinds of quantitative structural things we can measure or quantify, I should say, about structures and how they relate to things like deformation geometry or deformation histories. So that's this 2011 paper called Homogeneous Steady State Deformation, Review of Computational Techniques. Sorry about all the text here. I just want to throw out that I've done a lot of different things and I have a lot of different interests. Today, I'm really going to focus on the microstructural stuff, but I'm excited about and I enjoy collaborating to try and see how I can help. That's one of my things that, for better or worse, I find myself enjoying the most about research is thinking about how to help other people with projects. So I've done a lot of field mapping, landslide repair, GIS analysis, definitely a lot of microscopy and microbeam analysis. Lately, my specialty is really vorticity and deformation geometry, which may sound like gibberish to some of you that aren't structural geologists, and that's totally understandable. They're kind of esoteric parts of structural geology, but hopefully by the end of this talk, it'll make some more sense. I hope to cover a couple things today about similarities between microstructures and field scale structures, because I assume at least everybody here has at some point been out in the field, hopefully, and seen some rocks, maybe seen some shear zones, or thought about taking a mapping class and how there are similarities in the kinds of things that we measure at those scales and also at the microstructural scale. And how we connect those different scales that we measure things at and what's available as far as tools to do that kind of analyses. And then what I'm really going to dig into is how something called electron backscatter diffraction, or EBSD, has really, in the last decade, it's been around for a while, but in the last decade, it has come so far in its ability to be a much faster analysis, so it's more worthwhile, and also transformative for the kinds of things that we can quantify at a microstructural scale. And that has really allowed, that has paved the way for my entire career over the last 4 years. And so for me, it's a huge part of what I do. And we just put in a proposal a week and a half ago through NSF to upgrade our system here. So hopefully we're gonna sort of join the ranks of state-of-the-art EBSD facilities in the near future. And there's a lot still to work on. So I think, if nothing else, hopefully the things I talk about today serve as some kind of inspiration, or if you have some harebrained idea, I'd love to hear it. There's so many things yet to kind of work out of this. So this is our lab downstairs in room 126, the scanning electron microscope lab. I just wanted to show it quick so, maybe it's not as I've only met a couple of you down there so far, but feel free to come down anytime. I'm always either in this room or in 130, which is Dan and my office right next door. So here is the electron microscope that we have. It's a variable pressure microscope, which is kind of unique because it means that we can put samples in it without having to necessarily do all the same prep that we would do for a lot of other electron microscopes where we have to coat them and make sure that they don't charge as we're, so basically we don't have to put this at full vacuum to analyze things. So that's kind of nice. It's also unique in the world of electron microscopes because it has a remarkably big chamber. So this whole box right here pulls out and you can fit a rock about this size in there. Some electron microscopes, like the one that I just was using at the University of Minnesota before I came here, had a little exchange chamber on a bar. So you'd have to pull it out and nothing could be like taller than this and about this wide, and you had to push it in, and it was nice because you didn't have to kind of pump down between each session, but it meant that you were limited in what you could do. Whereas like just a week ago, some 7th graders sent me a rock that they wanted analyzed from Glendale, and it was this big chunk of gem silicon. We could just put it in there and shut the door and pump and start analyzing it. So, you know, if there's anything you see here today from imaging or something that you want to try, but you're like, I don't want to cut up my precious sample, let me know. There's a good chance we can just put it in there and start looking at it. So yeah, I kind of want to skip over this really quickly. The SEM lab is really, the SEM that we have was purchased to support the Arizona Lasercron Center because a lot of every sample that comes through there gets imaged for characterization before it gets analyzed with the lasers. And so that's a big function of our throughput and what we do in the lab. Another big emphasis is on support and training. So supporting your research and also training you to use the instrument. If you want to learn how and save money, you can, you know, the analysis time is cheaper if you're doing it yourself. And I really enjoy helping people learn about the world of electron microscopy. So that's a big focus for us. And outreach and in general, so like I said, I mentioned we had some 7th graders send a sample the other week. We were also reaching out to local schools to try and design workshops or other remote things where we can talk about what we do in both the ALC and the SEM lab in general. And then there's a bunch of things we can do from an imaging or mapping standpoint. And as I mentioned, we're hoping to get some new equipment. So we're going to expand on that too. This is sort of a close-up, or it is a close-up of our Hitachi SEM. And I guess what I want to describe here, I'll show another image, slide in a bit that gets at the anatomy of all of this. But for any electron microscope, we take advantage of sort of 2 different kinds of electron interactions. So what's happening inside the electron microscope is instead of using a light beam, we're accelerating electrons at a sample surface. And we get 2 primary different kinds of reactions. From this incident beam here shown as this yellow dashed line. One is called inelastic scattering, and the electrons that are the result of that interaction are called secondary electrons. And you kind of want to think about those as basically just bouncing off of some part of the atomic structure. Whereas the other kind of interaction we get is called elastic scattering, where electrons don't really interact, don't bump into something, but get deflected and come back out of the material. What's great about this, the fact that we have these sort of 2 different types of interactions, is they give us different information about the material that we're analyzing. So secondary electrons are really strongly influenced by the topography of the sample. So if you have a surface that's perfectly perpendicular to the incident beam, you get fewer secondary electrons being generated than if you have a high angle to it, where more of them can escape the surface. So what that means is that as we make an image of lots of electrons versus not so many electrons, we actually get a sort of an image that tells us about the topography of the sample. Whereas backscattered electrons are more influenced by the density of the material, because that scattering effect has to actually kind of go into the material and come back out. And so the more dense the material is, so in this case, they're comparing silicon and gold, the more scattering you get. So you get a brighter signal for denser material. So this is really good for crudely looking at the composition of, say, a rock or something. So this is an image that was collected by a grad student here, Maya, just a couple weeks ago now, of some microfossils, some forams that she was imaging. And they told me it was okay to use this photo, and I really appreciate it because I think it really highlights the effect of secondary electron imaging, where we can see lots of topography, right? Here, we're really just imaging the surface features, and you can see details of porosity and all these surface features and differences in texture on top of on the surface of this foram. And something that's unique about electron microscopy compared to optical microscopy is you get a remarkable depth of field of focus. So here, we're not, if you were doing this optically, you'd maybe have a depth of focus that only could really capture details at the upper surface, or you'd have to through focus. And there are great software packages for through focusing, like in a video, and then assembling some kind of 3D structure out of that. But in the SEM, we can see features almost down the whole side of this, somewhat spherical shape. So I think that's pretty cool. This is a full thin section backscatter electron map, where what you're actually seeing, all the grayscale contrast here is different minerals. So this is useful, even though we don't have anything quantitative about the chemistry of these minerals from this. We know generally that different contrasts are different compositions. So it's kind of nice for characterizing something like the composition of a rock roughly, or the microstructure from a compositional standpoint. And this is a full thin section, and I think this took about a half hour. We can push the stage really far down because we have that big chamber, and we make a mosaic where we take relatively fast images if you're not worried about detail, and we can map out the composition of your sample in a pretty quick amount of time. So as I mentioned, here's the figure of sort of the SEM anatomy, as I'll call it. The chamber, as I mentioned, this slides out and the sample goes in. And here's the electron column. Up here is where we generate the electrons, and our SEM uses a tungsten filament. So it's like a light bulb. It puts a bunch of current through a filament, and that is what is shedding the electrons. And then they're accelerated through electron magnets down through this column to impact the sample. And we can control the accelerating voltage, so how fast the electrons go, and that affects how deeply they penetrate into the sample, and also the amount of interaction volume we get, and the current, which is how many electrons are coming down per second. So both the speed and the amount. Inside here is where the secondary electron detector and a primary backscatter electron detector are. They're part of the sort of simple package of the Hitachi SEM. But we have some really wonderful add-ons that are these things dangling off the side of our SEM. On the right is the cathodoluminescence detector, which also has a built-in backscatter detector. So we actually have two different backscatter detectors we can use. Over here is what's called an energy dispersive spectroscopy detector. So this actually measures X-rays that we can generate by bombarding the sample with electrons. And the energies of those characteristic X-rays can be used to determine the chemistry at an elemental scale of your sample. And then here's the electron backscatter detector that we have. So I'll talk about these really briefly. So as I mentioned, there's different reasons you would want to use different detectors or different methods of detecting. And so here's an example from an ALC, a sample that came through the Lasercron Center of some heavy mineral separates of a detrital sample. So these have already been sort of filtered to try and hopefully have a bunch of zircons that were going to be dated. But we don't know if they're all zircons because we just separated them through a heavy mineral separation. And so the secondary electron image that we get isn't all that useful because this has been polished flat in a epoxy mount. So notably, or not surprisingly, they're all sort of the same grayscale here. Oh, and it doesn't show up very well, I realize, on the projection. But here, this backscatter electron map has a couple samples, or a couple grains like right here and here and here in between these spots that are darker. And we put standards on here that we know are zircons, and we sort of expect to have a certain response from. And then we can characterize what's the likelihood of any one of these things that we're going to zap actually being a zircon. So this is why we do this kind of imaging for all the samples that are coming through. It reduces time on the laser. It helps us understand the context of what we're actually analyzing. On the right is an image called a cathodoluminescence image, or CL image. And this is it's a little bit more time intensive to produce. But the thing that we get out of this is the electrons are actually causing a change that gives off light energy that we can measure. And so there's intragranular structures that we're seeing here that are related to trace element distributions. And so those are really useful context when we get down to the scale of a single zircon at the ALC and we're trying to zap different parts of it. If we're getting different information from different parts of the grain, maybe this kind of thing is useful. So that's.
Zach, quick question.
Yes.
Is each one of those a zircon grain on that plot?
Over here?
Yeah.
Probably some, yeah, I think so in this one. Sometimes you see apatites or something that light up kind of orange or yellow. And some of the things that are over here are not over here because they aren't responding to CL. So they're dark in there. But just to show a good, so this was a map I just made yesterday and sent to George because it was one of his samples of a more blown up image of a bunch of zircon grains that have been isolated and nicely oriented, and I made a CL map of those. And so you can see lots of internal zoning. There's different morphologies to that zoning, which is really interesting. And I'm learning a lot from the LaserCon folks because I'm not a geochronologist. I've dabbled, but these kinds of internal structures are telling us something about the history of crystallization of these minerals. And so it's great context as we think about trying to date them or different parts of them. The EDS detector over here, as I mentioned, is, so what happens is when we bombard an atom with a high energy electron beam, we get orbital changes, and those orbital changes give off characteristic X-rays, and the energy of those X-rays is characteristic of the material that they're interacting with. So what we do is we actually can make, we can do spectroscopy where we're counting the number of different X-rays that are hitting a detector and their energies, and make a real-time, or we zap it for a bit and we count for a while and we get a nice spectrogram like this. And we can raster it across a sample and make whole chemical maps of surfaces. One thing that's really cool about this is you don't need a polished sample to do this. So if you ever want to just put a rock in and zap something, or you have a grain of something, come on down, especially if it's something small. Maybe we can, if I've got time, we can just toss it in and see what it is, or at least get some chemical spectrum on it. Now, here's where hopefully this acts as a good transition. We'll see. This is our current Ebsd detector. As I mentioned, we're hoping to upgrade it and become a little bit more state of the art. But I love Ebsd. I love acquiring it. I love analyzing it. I'm obsessed with the kinds of things that we can do with it. And the reason is, during my master's, I started to go for more field scale things and integrate some optical microscopy, but I was plagued by the fact that it was so qualitative, the kinds of things that I was forced to say I couldn't measure very well. And when I got into my PhD and started studying periddotites and olivine, people do a lot of Ebsd analysis of olivine. And so I really had to learn more about it. And it opened my eyes to what a quantitative microstructural world there is if you have access to Ebsd data. So a little bit quickly about what Ebsd is. What we ultimately get are these pictures like you see down in the lower left, which are beautiful. These are called Kikuchi patterns. And they are, what you're seeing is there's a phosphor screen, like is shown up here in the left. And we have to tilt the sample at a really high angle to the incident beam. And what that allows to happen is the electron hits the sample and channels along the lattice planes in only the uppermost couple angstroms of the material. So it has to be crystalline for this to work because it channels along the lattice planes, and then it flies out in sort of a ball of electrons that are come channeling out of the surface. And those electrons hit this phosphor screen, and the bright spots are where you're seeing more electrons hitting the screen. And what that's actually doing is showing you something about the lattice structure of that spot that it's interacting with. And so here's an example from a cartoon that EDAX made of a rotating lattice and how those bands would change if the lattice orientation was changing. And so what we can do with this is map, even though it's a single 2D surface, we're getting a slight amount of 3D interaction with that material. We're able to map the 3D crystallographic orientation. And that is different from doing something like a universal stage where you can only get, say, the optical axis of a mineral. In this case, you're getting all the 3D information about the crystal orientation. What that's good for is you can actually not only get the orientation of a crystal at any point, but different minerals have different organizations of those Kikuchi bands. And so you can actually, through an image analysis that's built into the software that acquires this, you're able to index each point with a mineral. You have to tell it what minerals you think are in your rock, but EDS is really good for that, right? We can also hit it with the EDS and say, hey, I think we've got all these minerals in our rock. And you set that up as a list and you scan the rock and you can make maps like this. So on the left is a phase map that I covered with this inset, unfortunately. And over here is an orientation map. So you actually have at every single point a wealth of information about that single point. Its phase, its band contrast, which tells you about its sort of crystallinity, its orientation. And so we can make different images from that sort of multi-dimensional data set. It also becomes easier to query parts of your microstructure that are otherwise difficult to do from an optical image, where you have to maybe tediously, trace things or take a bunch of differently polarized images. And so it's very powerful. This particular map was collected by my colleague Seth Krickenberg at Boston College, who has one of the newer Ebsd systems. And this is almost a full thin section and contains just over 12 million data points. So our current system here can collect about 4 points a second. The system that we're trying to upgrade to collects about 1,200 points per second on geological samples. On metals or something, you can get up to 4,000 points a second. So the hope is that we're going to be able in the near future to make maps like these of any rock. This is just another gratuitous example of the kinds of maps we make from these. And in this case, they're all colored by phase. But what's really great about this is you don't even have to, let's say you were interested in all the K feldspar grains for maybe you're interested in some kind of shape preferred orientation or some aspect about these minerals. You don't even have to take this image and do some image analysis on it. You can just, through interacting with the data set, isolate those bits and then analyze those separately. So, okay, now I'm going to try to talk about some microtectonic stuff. I think that set the stage pretty well for what we have and what we're trying to do. I know there's a world-class tectonics research program here, but I want to just cover a couple things that are important as we go forward about what it means for a rock to be a tectonite. So a rock that has been tectonically deformed, because it's going to become important for the rest of the talk. So when we're talking about tectonites, I'm talking about a rock that has undergone some kind of deformation in a geological setting. And the rocks that I focus on have been deformed in the solid state. So they creep, meaning the deformation is not fast, they're not molten at any point or at the point that they're flowing. And there's two ways that can happen, either by diffusive mass transfer, where material is diffusing from regions of high stress to low stress, or by what's called dislocation creep, where inside the crystal lattice, you actually have discrete movements of the lattice plane across unit cells under stress. A major, one of the more exciting things about tectonites is that they have fabric to them. And by fabric, I mean some kind of pervasive alignment of features in the rock, like minerals that maybe are elongate and all point in the same direction, or for example, micas that form a foliation. So we're really talking about any rock that is well foliated and lineated that was deformed in the solid state would fall into this group of tectonites. And we have some terminology here I don't want to dwell on. I realized as I was trying to set up this talk that what I really want to do is teach a whole class about this. So I know I'm kind of driving through this, but anyway, we have some terminology that's pretty straightforward. L-tectonite means you don't have a good, you just have lineations, no real planar fabric. An S-tectonite means that we have a good foliation, but not really much to see in the way of alignment of minerals to define a lineation. And then what are really cool and really useful in a lot of cases are LS tectonites, where we have both. There's also these fabrics sometimes at a macroscopic level are hard to see, but there's often a microscopic effect too that we can interrogate, where we get alignment of crystal axes. So maybe the grain shapes don't tell us much, but if we're able to analyze, say, using Ebsd, the crystallographic axes, we see a strong preferred alignment of those that was the result of deformation. We can also do things like look at the grain shape in a very detailed way. So sometimes you see strung out ribbons of quartz or something, but at a really close scale, they're made up of a bunch of smaller grains, and those angles of those shape preferred, or those grain shapes, can tell us something unique about the deformation geometry. All right. So what microtectonics means to me is really just taking all this kind of structural petrology knowledge about how we look at fine scales of composition and structure and apply them to tectonic questions. Specifically to my interest is how we go from something like an outcrop to a thin section and back and forth, and actually infer confidently something about the kinematics of that shear zone. And before I got to Madison, my thinking about kinematics and fabrics was, I don't want to say simplistic, I want to say pretty standard. I think it's what how a lot of people approach it, with the sort of rule of thumb that lineations point in the shear direction. Boom, I know, I go out and I map this and I know what's going on. And it was working with Basil Tikoff at Madison, who thinks a lot about different strain geometries, that I realized how untrue that is, and it terrified me in some ways. But so this is where a lot of my research has gone. But also concerned in this is the timing of things, right? Either relative or absolute timing. And so the chronology and the evolution of each of these fabric elements and the kinematics of shear zones is of great interest to me. And one of the things I'm really excited about being in such close contact with the folks in the ALC working down in that lab is already formulating ideas about how we can study the 4D evolution of shear zones. So I want to point out too that one of the reasons I'm so excited to be here is because this department is just uniquely primed to tackle some of the really exciting emerging questions in both geochronology, microtectonics, and unite those kinds of things. And so I think that if anything here sort of gets you excited, that's at least my intention, because I'm excited to be here. And what I've been working on the last few years is really how there are feedbacks between microstructural evolution and the rheological properties. So basically the strength of the rocks that are deforming, and how changes in microstructure during deformation have a feedback on the strength of those rocks, which is important as we think about tectonics, right? Because we want to know why and how a shear zone localizes and forms where it does. And then why does it persist for so long? What makes it able to be reactivated millions of years later? All right. And so a lot of the things that you've maybe learned from field scale structural things or from mapping classes really are pretty easily applied at the microstructural scale too, whether you're looking at offsets and cross-cutting relationships, things that are really familiar. And probably most of you, if not all, have looked at a deformed rock in optical microscopy, and it's nice because that can be pretty fast. You maybe got to get some thin sections made, but you can just stick it in there, move around, look for what you want to find, take some images, make overlays. And you can be quantitative with those, right? You can do some measurements on those or thresholding and use either a computer or by hand to do some metrology. But sometimes that's tedious. And so, as I mentioned, and I'll get to, the world of Ebsd makes a lot of that so much more tractable. If you have the means to collect those data, all the kind of things that you sit there and go, boy, I'd like to do this, but I don't want to spend 4 hours tracing all the grains in here to measure their long axes. That's the kind of thing where, well, maybe we just put it in and map the thin section for 4 hours, and then you have all of that at your disposal. Some of the tools that we use are optical microscopy, microbeam analyses, like I've mentioned, and in general, which is why I included Renee's book in that first slide, image analysis has become something I'm part of my toolkit I sort of never really imagined for myself. And I do a lot of the Ebsd analysis in MATLAB, and MATLAB has a really strong image processing toolbox. And so they work well together. So a crucial part of any microtectonics study is trying to work in different reference frames. And this becomes really important because you want to be able to maximize what you're getting out of any analysis. And so you may have to cut a rock differently than you would see it in the field, or differently than the fabric looks like to get at the things that you want. And so specifically today, I'm going to talk about geographic reference field, which I think is pretty familiar to most people. This is where you go see the rocks in their natural habitat, in situ, versus the, say, structural fabric, or structural reference frame, where maybe we're talking about the fabric in the rock or some structural feature that you sampled the rock from, versus the kinematic reference frame. And these two, I used to think were basically the same. And I'm going to try to explain to you today how they're not, and why that became an obsession of mine, and how that basically helped me finally finish my PhD and has defined my career somewhat since. The geographic reference frame. So, this is getting at the fact that rocks that are still intact and in situ, we want to measure any of the things about them that we can while we're there. That's crucial for any microstructural or microtectonics research. And we've all had experience, I think, or I keep saying that. I don't want to make it sound like if you haven't, you're weird. If you've done any structural geology or mapping, you've probably had a Brunton out there and measured some orientations of things. And maybe that's as far as you've gone, and then thought, okay, now I'm going to plot this on a stereo net or something. But what we really want to do is, when we take a sample out of there, we want to make as many notes and marks on those rocks as we can, so that we can know as we cut it up. Basically, you want to be able to hold it up in space in exactly the way it was in the outcrop. And I don't actually do that with my rocks, but you want to have enough information that you can. And so what we do is we collect samples in a way that we call oriented samples, where and there are different conventions for this. This is one that Mikabayashi put in a paper, and I just think it's useful because it's cool. It's better drawing than I could do. But the idea here is these lines, like on the top of the rock, are marking a preferred orientation lineation of minerals. And these horizontal lines are marking a foliation plane that go around the edge of the rock. And so we can orient the rock and then cut, let's say we want to look at the microstructure and cut a thin section. We cut that thin section relative to some feature in this rock that we've measured. So then if we want, we can restore it to the geographic reference frame. The other thing great about the geographic reference frame is, let's say you collected this rock in one place, but what you were really interested in is not how the data look on a map, but relative to, say, a shear zone boundary or something that you mapped elsewhere. Well, then the geographic reference frame, because you measured both of them in the geographic reference frame, acts as a link, a go-between for rotating those data. Okay, the fabric or structural reference frame is really getting at, so this was kind of both, right? You have the geographic marked here by strike and dip symbols, and then you're cutting the sample relative to the fabric. Sometimes you don't have the geographic reference frame, or what you're really interested in is something about the fabric formation. So in a lot of cases, our default is to cut sections that are parallel to the lineation. So here's this perspective view of a thin section coming out of this face where we have lineations look like these dots going into the block and the foliation trace is here. And so we cut a thin section that's perpendicular to foliation, that's this perspective plane, and parallel to lineation, like these little red lines. And then maybe we collect some crystallographic data using Ebsd. And so here we're plotting, this is in the case of a xenolith being plotted in, so olivine, showing the A, B, and C axes of a bunch of crystals in the sample, and looking at their patterns here. And I just mentioned xenoliths, and that's another great example of when you are going to probably cut a rock relative to anything you can see, because you have no context, right? It came out of a volcano. The shears, if it's a sheared rock, it was sheared down in the mantle or something, or in the lower crust. And so you have no context for the structure that came out of. But maybe you can see olivine, like in this case, these are peridotite xenoliths. Maybe you can see an olivine grain-shaped fabric, and you could cut it relative to that. Sometimes, especially in peridotites, you don't, like dunites don't have a screaming fabric to them a lot of times. So one of my colleagues, who was a postdoc when I was at Madison, we shared an office, developed this, Vasilios Hatsaris, developed this technique of putting a xenolith in an X-ray CRT machine and scanning it to find high density minerals like spinels, and map out a sort of preferred ellipsoid that matched the orientation of spinel trains, and use that as a best guess for a finite strain ellipsoid or some kind of fabric, and then basically reorient the rock and cut it relative to that. So there are ways to work around that, but really this is just as an example of how you may have to work with the fabric and have nothing else. But I think I'm going to explain why the kinematic reference frame is really the most useful, or where I see always my target. So this is a figure that Basil Tikoff put in a review paper in 2013. And I was helping draft it for the paper with him. And I was just sort of getting into this whole world of different strain geometries. I'd always thought about everything as simple shear or pure shear. So non-coaxial, like cards sliding in a deck, or coaxial, like squishing or pulling on something, right? But what we know this from field examples and from strain models, that so all of these little block diagrams are shown relative to the kinematic reference frame. And what I mean is that this oblique right side is in every case a vorticity normal surface, meaning that whatever coaxial component of deformation, like the rotational part of this deformation, is coming out of this side. It's this red line. But depending on whether it's entirely simple shear, or you have some strong component of coaxial deformation, you can get lineations that either point in the direction of shear or point perpendicular. So they're vorticity parallel here. So if you went and you cut this rock like this, and you wanted to analyze something kinematically, you'd be looking in the totally wrong reference frame. But how would you know? And then to make it even more confusing, when you have things like transtension, you can actually get foliation planes that are, in this case, normal to the vorticity vector. So you might think, oh, everything was sliding like this, but you're off entirely in sort of your perspective just by looking at the fabric. And that, I'm just going to mention that triclinic deformation is a whole other ballgame, where they don't have, these features are not going to be aligned orthogonally. They're going to be at some angle, and interpreting that is really difficult. So to kind of drive it home, you can have the same direction of movement, but very different relationships to the fabric. All right, so what I did during my PhD, I'm moving ahead because I don't want to run out of time, is I was starting to work with olivine, and I was really concerned about this because olivine, through experiments, has been studied in a deformation geometry where all of these different crystallographic fabrics are plotted, and they were done at different conditions, and different conditions yielded different fabrics. But if you don't actually know the kinematics, you could take a rock from one orientation and have cut it the wrong way and get a different fabric than you should. So at the time, or about a decade before, there was some work on calcite where folks that did a lot of Ebsd analysis were qualitatively saying that the interiors of big grains like porphyroclasts had a rotational axis that they thought, these were in calcites, matched the vorticity axis. So I thought, oh, this is great. And so I wanted to try to start using Ebsd to see if I could objectively get at the vorticity axis. So in this case, I took a large kinked pyroxene grain where I basically knew from the really clear, large kinking what the kinematics were. And here's an Ebsd map where we see a change. This color is showing a change in crystallographic orientation across this kink. And here's some little cartoons showing 3D cartoons showing crystal orientations. And here's the A, B, and C axes of this clinopyroxene grain. And you can see that they're dispersed about some kind of rotation. But how to measure that? And it turns out that if you actually take what I thought right away, oh, this would be simple. I'll take one axis, I'll do like a principal component eigenvector analysis, and I'll get a rotation axis. But it turns out if I did that for each crystal axis separately, I got different answers, which is nonsense, right? It should be one best fit rotational axis. So this was what I was going for. I had in my mind that the lattice orientations are, or that the lattice itself is curved due to deformation in some way that's causing this dispersion. And I want to analyze this dispersion, but instead of getting three different answers, I want one answer. So at this time, Joshua Davis, who I mentioned, who was at Carleton would come down to Wisconsin and visit with our structural geology group and talk about quantitative analyses that we could apply. So he's a mathematician. He was helping us become more quantitative. And I kept asking him, hey, I have this problem and I don't know how to do it. And it was funny because he kept saying, well, I just don't get it, why you want to do it. And finally, one night I'd harassed him enough via email that he's like, well, I know how to do what you want to do. Here's a script in R to do it. And I got all excited and I took that and I rewrote it in MATLAB. And the difference is it's similar to a principal component analysis, but it's called a principal geodesic analysis. And what this does is you take the mean orientation and you project the data from the orientation space, which is non-Euclidean, into a manifold Euclidean space and do a principal component analysis there, and then pull it back to the rotation space. And you get a single rotation that best fits the dispersion of a bunch of 3D orientations. So what we discovered right away is that, so I started applying this to grains and samples, and I realized that every grain gave a little bit different answer. So I was like, well, this doesn't, what about big grains? Same thing. So I almost gave up on it. And then I was actually talking to Alan. So Alan and I were both at Wisconsin for a bit, where it dawned on me that I don't want to give this up. I really want to dig into this more. And so what I did was write it took a long time and now it's faster, a loop that would go through every grain and analyze every best fit rotation axis and then plot them together. And we did this on samples from some well-studied shear zones, like the Moyne Thrust, Gem Lake Shear Zone, and the Western Idaho Shear Zone. And these two are both simple shear, subsimple shear, and they were cut relative to the lineation and foliation. And so we sort of expected to see this kind of bullseye right in the middle, right? It's rotating around, you're sliding like this. In the Western Idaho Shear Zone, there was a lot of evidence that that people had already mapped that there was a lot of coaxial deformation and that lineations were maybe actually recording a vorticity normal or a vorticity parallel orientation. So again, we cut the rock relative to the lineation and we did this CVA, what we called crystallographic vorticity axis analysis. And lo and behold, it mapped to, we got a bullseye that was lineation parallel. So this was our clue that maybe it was working. So we started running with scissors at this point, and we started applying it to field scale things to look at changes of a long strike deformation geometry. So this is from the Western Idaho Shear Zone. I started working with Seth on some myelinites in the Appalachians and rotating the data to the geographic reference frame. That became a big part of my research. And we got excited about here's the results from different phases. And it looks like they're all pretty much telling us the same thing. So this was exciting because it suggested we could use it on a bunch of different phases. I'm going to really quickly and then stop, just mention that what I've been doing in my postdoc is prior to here was deforming olivine samples in an experimental apparatus in different geometries. I'm only showing torsion, which is like trying to get to high strain simple shear by twisting it and then looking at a tangential section, and compression and tension. But I've since then done some combined load experiments that I won't have time to talk about today, where we were enacting transpression and transtension. And what we saw is that the patterns in the CVA axes, the axes of most rotation, were different for different strain geometries. So this was exciting because for simple shear, we were getting what we thought we would get. But in compression, we weren't totally sure what we would get, although I'd sort of predicted this, that we get like girdles of rotation axes that are helping accommodate flow outward everywhere. Or even though it was a bit weaker signal in tension, something similar. One thing that I'm excited to, and I was just talking to Sharing, who left for the field today, about other strain geometry things that we can do, is the result that we get from the CVA analysis is a tensor, meaning that it has principal axes to it. And the CVAs that we talk about a lot are the axis of most rotation, but there is an axis of least rotation too. And I think from the experiments that we've done, there's some suggestion that that's actually helping us understand something about the flow apophyses and flow directions during deformation. So that's something that is very hard to know from rocks. And so it's exciting to me because this might be a way that we can use that in conjunction with other field evidence to say, hey, maybe this is a new tool for really putting both of these together and helping constrain the strain geometry. Time have I got? Oh yeah, I'm gonna stop. There's a lot here. I'm sorry, I'm just tearing through it. And I was overly ambitious, but I wanna, before I open up for questions, I just wanna say that I wanna be here for you, for anything that you wanna talk about. I'm down in that lab all the time or in my office. Whether it's imaging, or you want to brainstorm more about some of these ideas, or if you have ideas, you're like, hey, he's totally missing the boat, he should be doing this, let me know. I would love to hear that, and we can collaborate. So I'm excited to be here. I really appreciate the opportunity to tell you about this. I'm sorry if it felt like drinking from a fire hose, but let's chat and let's collaborate. So thank you. So we do have some time for questions. Go ahead and jump in. Yeah.
Actually, as a preface real quick, for EBSD, are you just using polished thins, or can you use polished grains in amount as well?
Anything that's polished well enough will work. Yeah. So
Can I ask you to repeat the question for the people?
yes. So the question was, can you, for EBSD analysis, do you need to have polished thin sections, or can you use a polished single grain or other analyses? And I've done EBSD like with John Valley's group. We did it on some diamonds that were just gem mount, basically gem quality diamonds. And actually, depending on what you want out of it, if you want a nice map, it should be polished to some extent. But if you just want to try and get a single orientation out of like a big gem, we could probably hit enough spots where we finally get something to index, and then its orientation. Yeah, and the one thing that is unique about EBSD though is because it interacts with the uppermost couple angstroms, the polish is critical. So for when we are polishing thin sections, even if you have it like polished for the probe or SEM work, what we really need is a mirror polish. So, back when we were doing it at Madison and then by hand more or less at University of Minnesota, we would get down to 0.5 micron laps. And then for olivine and some minerals, it's important to actually etch it afterwards so that you remove that slight amount of damage that's at the surface from the polishing, so that the electron beam is interacting with sort of fresh crystal lattice.
Are you set up to do that kind of polishing here?
Yes and no. So we're set up we can do it, but one of the things that I've been looking into is how we can get set up to do it more regularly. So we have the right things that we could make it happen, but there's we have a vibratory lab up in the lab that we have for ALC and picking lab. And we can get the right solutions for that and put them on there and let it just go for a while. So we can. The other thing that, and I still haven't talked to the right people about this, is down in the basement, or sorry, on the ground floor in the annex, there's a set of lap wheels, and they don't seem like they're being used. And even though it would be a little bit more, it would be more manual, that's sort of the world I just came from, where we were making our own little experimental samples, and then we just have a series of lap films that we'd go through, and that takes about, 20 minutes to get through maybe 4 different films, and then do some like Cyton etching for a half hour, but then you have a pretty good sample. My hope, especially, so I'm gonna have to get our act together once we anticipate this upgrade, to have something where we can maybe mount, I know at Madison, we were able to get up to like 6 thin sections on the vibratory lap. And so we could then kind of do them in little sessions, and you could, get a box of thin sections done in a week or something, which is a lot harder by hand. So yes and no. But we're gonna work towards it. Yeah.
Students to know about the magnification and resolution of the SEM. So, are we able to analyze the nanometer scale?
In our, so we are.
You can repeat the question, sorry.
Yes, sorry, right. The question was regarding what is the resolution of scale on our SEM for the kinds of analyses that we've been talking about. And our SEM is a tungsten filament, and it has a bigger spot size than you would get out of something like a field emission gun source. And so that limits how low we can get. I had a student in here, so I've only been here a couple months, but one thing that was really fun is the student came from microbiology and had some bacteria that she wanted to look at. And so those were on the scale of about a micron in diameter, and some of them a little bit less. And we were able to resolve that they were there, but we couldn't see much details of that. So we can get down to the scale. Basically, once you get down to the scale where like your scale bar here is a micron, it starts to get a little bit fuzzier. If we spend, for those kind of analyses, if we take the time to do a really good alignment in the morning, and basically we can get better images. The nice thing though about this is a lot of these techniques like the Ebsd, the software controls the step size. And so even though your interaction volume may be bigger than your step size, there's enough difference that it's analyzing at each of these steps that you can actually resolve data sets that are better than the images you would get from the electron image. So it kind of depends on the analysis you're doing. If you're really interested in nanoscale stuff, so what I would say is let's try it, because that's something I'm interested in, pushing the limits of this. But then if we can't do it here, the good news is that the Lunar and Planetary Labs has a couple different electron microscopes, one that's just like ours, and 2 that are field emission guns, where you can resolve better scale. So our lab is cheaper to work in, and if we're just trying it out the first time, just bring it in, I'll test it out for free, and then we'll take it from there and see if you're seeing what you want, then we can work here, and if not, maybe you can work over in LPL for something. And they also have an Ebsd system there too.
And you mentioned that the backscatter electron microscopy giving us the density of the.
Yes.
So does it give the quantification of density, or does it give like low height?
Sure. So the question was, I mentioned that the backscatter imaging gives us a sense of the compositional contrast and the density based on density. And the question was, do we have any quantifiable information from that? And the answer is really no, because what you get is a grayscale image. And for every setup, every different material you put in there, you might threshold the brightness and contrast differently, so that range is sort of fluid, and you try to maximize it when you take the image so that you get, near black and near white, but you don't max anything out, and so you get as much range as you can. Or if you there's certain things you're not concerned with, maybe you threshold those out. But basically your 0 to 255 grayscale image level that you get out is arbitrary, or it's based on what you did when you imaged it. So, but that's where EDS, the energy dispersive spectroscopy, is useful, because we can actually use the characteristic X-rays to try and map the chemistry at that scale too. So the software that we have for that lets you use the backscatter image from the SEM as a map to target points. So you could sort of, or what we do is we take a backscatter image where we are highlighting different compositions, and then we either make an EDS map or some point analyses of those different spots. And then we can say that, that could act as your key. Let's say you map a whole thin section in backscatter, and then target a spot for some EDS, and you say, well, all the bright things are zircon and all the dark things are this. And then you sort of have a key from which to interpret your map that you made. I mentioned too that I do a lot of image analysis, and I primarily use MATLAB for that. But one of the cool tools or things about the image analysis toolbox in MATLAB is you can easily bin through sort of a clustering method, different grayscale levels. And so if you thought you knew, oh, this heather gray is like one mineral and this really bright gray is a different mineral, you could then colorize a grayscale map using those sort of values. So there's workarounds, but it's not quantitative itself.
There's a question from the chat from Jordan. Jordan says, hi, Zach. For a sample that may have undergone 2 different phases of deformation, say a tectonite formed along the thrust fault that was later reactivated as a normal fault, would CVA detect only the youngest vorticity axis, or would there be evidence of both?
That's a great question. Do I?
No, this is on the chat, so no worries.
That's a great question. And it's actually something that I've been working with folks on a lot lately. So in general, I would say that microstructures are more quickly reset than sort of finite strain things that we can see. And so more often than not, the CVA signal seems to reflect the latest stage of deformation. There was a student from Kyle Larson's group that I worked with up in UBC who wrote a paper about looking at relic porphyroclasts that survived a couple stages of deformation. And I wrote for him a sort of sliding window CVA analysis, which would, instead of getting 1 point per grain, we would get a bunch of little windows of CVA results and then map those results relative to the perimeter of the grain. And what he argued that he saw, and I sort of agree with, but I think it's a little messier than this, is that near the outer perimeter of the grains, there was a different CVA signal than there was in the center. And he argued that he thought that that more peripheral one was more likely, or I would agree that it's more likely the result of the later stage of deformation, and that the more insular one was telling you maybe something about the previous deformation. Now that I've done a lot of deformation experiments, I'm a little bit skeptical of that, because this CVA analysis relies on dislocation movement. And what happens is, even though we see the end result of some intragranular lattice distortion, there's during deformation, there's dislocations shooting through these grains from one side to the other. So I'm a little skeptical that I would expect to see something so different in the center, and that maybe what we're actually seeing is some stress concentrations around the outside. My gut is that CVA is really most useful for the latest stage of deformation. Yeah.
I got a quick kind of logistical question. I'm not that familiar with Ebsd before. I have colleagues that have used it, but
Sure.
so am I correct in assuming that you have to have a thin section for Ebsd? So I have colleagues who work on bivalves, for example, and they've used Ebsd to see if pristine aragonite has been transformed into calcite with diagenesis.
Yeah.
And so that could be something that our group does. We do analysis based on stuff like that. So I'm just wondering, is it gonna be destructive in the sense of having to make thin sections, or is it possible to actually put whole shells in? Or how would that work?
Right, so if we put a whole shell in there, it might be that we could zap it enough that we get a couple results in spots, but if what you want is a map, we're gonna have to have a well-polished surface. It doesn't have to be a thin section. So actually, it's great for thick sections, right? Because it's just interacting with the uppermost bit. So you're not trying to get any transmission. So you can have a thick section, but you're gonna get the best. What we should say is you want a polished, flat surface. And because it's interacting with, it's at this high angle, any surface topography can really mess up that signal or make it so it doesn't index well, or the channeling is bad, or it shadows another part of it and you're missing parts. But I have done some EBSD with Ben Linsmeyer at Madison on different fossils. I helped Seth. I thought this was really cool. This is just maybe this is helpful for thinking about why it doesn't have to all be about microtectonics. There was a group at Boston College when he got there that had, I want to say it was like an ostrich egg, some kind of egg. And their question was kind of fascinating. It was like, what is it about an egg that makes it protective from the outside so that these little critters are protected, but weak enough that they can peck their way out, right? How is it that the inside is weaker than the outside? And so they were talking to him about it, and he's like, let's just make a really small section of it and polish it up. And so they took a cross section of this eggshell and saw that the calcite that was forming this shell changed on the inside. It was very small, fine grained, and had a random orientation. And then the growth of the shell had given way to a well-oriented C-axis alignment of the calcite. And so the interpretation after that was that this crystallization front allowed the inner part to be weak because they could sort of propagate cracks through it, and then yet the outer part to be coarse-grained and stronger. So I think that there are interesting microstructural questions that may be neat in other people's research that I'm just not thinking about. But if you think, especially as we get more advanced in our capabilities here and we can do things a little faster, if you have ideas, like, let's try it. I think that, it can't hurt to try. But you might have to destroy a sample. All right, thank you.
I think we're done. Thank you very much.
Cool.
Okay, can I just make an announcement? If you're leaving, which we all are, you could just turn your tables such that each pair faces each other. That'll help the graduate students who are working on doing this afternoon. So thank you. R goes to the so just find R and L.
That's not yours. No, it's not mine. Perfect. That was great. Thanks. That was fun. Yeah. Got everybody interested, excited, tickle their fancy. Yeah.
Grain size. Okay, so you mentioned seeing like you got the big appearance scene that has that big stuff. Is there a preference for larger grains? So in that case, it's like so strain unit. But if you have something that's really, if all you're working with is fine grain stuff, kind of like with Backscatter, your zoning is more interesting.
I have a multi-directional microphone, which you're welcome to use for this.